Jnanam Paramam Dhyayam. Knowledge is supreme.
Today I will prove what is called dimension theorem, and I want to prove it for modules actually. So let us set up the notation. So we have a ring A. A is a local ring, and V is an A module, and we will assume V is finite A module. Then we have to the module we have the support. So support of V as a module. This is by definition all those prime ideals P such that V localized at P is non-zero. This is called the support of the module V, support of V. And you would have seen in earlier course that this is a closed set. This is V of annihilator of V. This is a closed subset of the spec of A. Remember when we say spec of A, we consider the Zariski topology on that, then this is a closed subset. So, and the dimension of Krull dimension of V is by definition the supremum of R, so that we have a chain of length R in the support of V. This supremum is called the Krull dimension of V. So, if V equal to A, then this is the definition of a Krull dimension of the ring A. V equal to A, this dim A is what we have been talking in earlier lecture. This is the Krull dimension of A, because in this case support is the whole spectrum. Support of A is the spec of A, and I have been saying that a priori it is not clear that this supremum is finite. So, we will prove today it is finite if this ring is local, and in that case we will have another two definitions of integers which are attached to V. So, also I want to remind you the convention. The dimension of the 0 module is -1. Okay, the another definition is, and also I am assuming V is non-zero. So, in this above V was non-zero, V is non-zero. So, that is why we had to make a convention, dimension of a 0 module is -1. So, also we define now, look at the another number which is called a Chevalier dimension, that is S of V. This is by definition infimum of integer R such that there exist R elements in the maximal ideal of A such that when you go mod ideal generated by A1 to AR in the module V, that is length of V modulo A1 to AR V, this is finite. So, that means this residue class module V by A1 to AR V, this is of finite length. This is called Chevalier dimension of V. This makes sense because certainly if I take A1 to AR to be a generating set for the maximal ideal, then this module is V by MV, and obviously this is a finite length module, because in this case this residue class module has a support only M, and one tests that a module is of finite length when the support consists of maximal ideals. So, also we will put by convention that S of 0 module is minus 1. This is convention. And remember, we have already defined d of V. D of V is by definition the degree of the Hilbert-Samuel polynomial PMV, or for that matter PM P Q V, where Q is any primary ideal, M primary ideal. And we have checked that this degree does not depend on the primary ideal you choose. So, you can take whichever primary ideal we need to take. And the theorem says now these three numbers are same. This is called dimension theorem. It says that dimension of V equal to d of V equal to S of V. In particular, dim V is finite. That is because it is a degree of a polynomial, or also this also it is clear that this SV is bounded by, for example, the minimal number of generators for M, and because we should also assume, when I say local ring, by definition that it has only one maximal ideal and it is Noetherian. Noetherian is also part of that definition of local ring. So, we will prove this theorem. So, proof of the plan of the proof is, we shall prove the inequalities dimension of V is less equal to dm is less equal to SV is less equal to dimension of V. So, this will prove their equalities. This is, let us call this as 1, this is 2. So, we have to prove these 3 inequalities. Okay. So, the first one, proof of 1. So, first let us dispose of the case, suppose dm is 1 minus 1. That means this module M is 0. No, not 0, but dm is minus 1 means, so that is the degree of the Hilbert-Samuel polynomial is minus 1. But that means m by, that means 0 polynomial for large n. So, that means m by m power n m is 0 for large n. But that means m is 0 by Nakayama lemma, because we are in a local ring, m is a finite. Oh, why did I change it to m now? V. So, this is V and this is also V, everything is V here. V is 0 by Nakayama lemma. But if V is 0, then we have put by definition d of V is minus 1 by convention. So, that proves this inequality. If this is minus 1, this is minus 1, that is what we have proved. Now, assume d of V is bigger equal to 1. So, that will imply bigger equal to 0. That will imply V is non-zero, and that means support of V is non-empty. So, there exists a prime ideal P. So, that implies there exists a P in the support such that dimension of V equal to dimension of A by P. Remember, we have put this dimension to be dimension of V to be the length of the chains of the prime ideals in the support. So, I take at the left end, I take the most, so that we cannot go on further. So, that is dimension of A by P, because if the lower end of the chain is some prime ideal P, I choose so that it is maximum attained there. So, it is dimension of A by P. In fact, this P we can choose in the associated primes of V. Because you remember the minimal elements in the support and minimal elements in the associated primes are same. So, therefore, if P is in the associated primes, so that means A by P is a submodule of V, because associated prime means it is the annihilator of some element, and so it is A by P. A by P is a submodule of V. So, that will mean that the degree, remember when somebody is a submodule, in the last lecture we have seen the lemmas that the degree of the Hilbert-Samuel polynomial for A by P and degree of the Hilbert-Samuel polynomial for V, this is less equal to this. So, with this it is enough to prove. Now, to prove the inequality 1, it is enough to prove that if I have a chain like this, P equal to P0 containing a proper chain of length R, then this R should be smaller or equal to d of A by P. So, this we shall prove this by induction on R. This by induction on R. Okay. So, if R is 0, then there is nothing to prove. Then nothing to prove. If R is bigger or equal to 1, then choose an element A in P1 which is not in P0, that you can choose because the chain is proper, and consider the exact sequence 0 to A by P0 and multiplication by A by P0, multiplication by A on A by P0. So, this makes sense because this is a multiplication by an element A, and this element A is not in P0, A by P0 is an integral domain, so A is non-zero element there, so multiplication map is injected, and the co-kernel is A by P0 plus ideal generated by A. So, we have this exact sequence, and then once we have an exact sequence, then we know that D of this P0 plus A is strictly smaller than D of A by P0, since we have proved that if I take the alternating sum of the Hilbert polynomials and take the degree, that degree is smaller than the degree of the middle one. So, since D of Pm middle one, that is A by P0 plus this one Pm A by P0 plus A minus Pm A by P0, this degree is strictly smaller than degree of the middle, that is Pm A by P0. But you see, this is same polynomial, so the leading coefficient will get cancelled. So, therefore, this degree is smaller or equal to this degree. So, that is what it means, that D of that is strictly less than this. Okay, now, once you have proved this, now choose prime P0, P1, P prime in the associated primes of A by P0 plus A. Remember, I am trying to choose sequence of elements which will generate so that the module V by those elements will have a finite length. So, this choose associated prime P prime of A by P0 plus A such that P1 P prime is contained in P1. Remember, this ideal is in between P0 and P1 because A was in P1. So, P1 may not be associated. So, I choose a prime which is contained in P1 and which is associated prime, and look at this sequence. Now, I remove P0 and P1 from the chain and look at P prime which is contained in P2. This is not equal because this is contained in P1 and so on. Look at the chain. and now by induction that r minus 1 is this length is r minus 1 because it starts with this is starting with 1. So, its length is r minus 1. So, this is less equal to d of a by p prime by induction. And now you look that this is the associated prime. So, there is a injective map, this is a by p1, a by p prime is a submodule of a by p0 plus a, and therefore, d of this is smaller or equal to d of this. So, now we have inequality. See, this is this one, let us call this as 2, this as 3, and also we have proved d, this is 1. So, r is less equal to d of a by p, and this I want to combine to get r minus 1 less equal to d of a by p prime, and this one is less equal to this one d of a by p0 plus a, and this is now the last one, that the first one, that is d of a by p0 minus 1, because that one I shift to the other side. So, therefore, altogether that implies r is smaller or equal to d of a by p0. That is what we wanted to prove, that is the first inequality. So, I proved that if I take any chain of prime ideals of length r in the support, then that is bounded by this degree. So, therefore, that proves that dimension of V is less equal to d of m or d of V, because we have chosen P0 with that property. Okay, so that proves the first inequality.